Okay, all right. So funny thing though is that when you begin to look at some of nitrogen isotope fractionation of nitrogen in cells grown in the laboratory, gosh, you can produce whatever fractionation you want. It's basically the delta 15N value of nitrate. It's a change in the nitrogen from the initial value and the log of the concentration from basically the amount utilized. And here's 5 per mil, here's 25 per mil, kind of in the middle of the isotope fractionation associated with nitrate reductase. So, and we got nice relationships between all of these, but the slope varies a lot. And so, how do you make sense out of something like that, where in the field we see nice consistent relationships, but in the laboratory, gosh, we can produce almost anything we want in terms of a slope, which is indicative of the fractionation associated with assimilation. Okay, a key observation in this study, which is by Julie Granger and others, is on the right. And that shows the delta 15N value of nitrate versus the delta 18O value of nitrate. And there's a one-to-one line. And it turns out that all of these data that show these really, really different slopes, really, really different fractionations, collapse on one, a nice linear relationship. And that tells us something. It tells us that the major step in assimilation of nitrate by phytoplankton has one dominant fractionation mechanism. And this relationship between 18O and 15N gives us clues to what that should be. It should be equivalent. It should be a ratio of 1. Well, we can look at, well, we can't, but we can sort of wave our arms and say, well, what would you anticipate the nitrogen isotope fractionation versus oxygen isotope fractionation difference be in terms of nitrate diffusion? And it's difficult to get away from any kind of calculation that is greater than about 0.5. So it's probably not diffusion that's a controlling factor on this relationship. We can look at, or calculate actually, the thermic NO bond. You can increase the temperature of nitrate till you break that bond, and it's a calculation you can make, and the ratio is about 2. The only one that fits is an observation that tells us that the 15N fractionation versus the 18O fractionation associated with nitrate reduction is 1, and that makes sense. So what is dominating the isotopic fractionation associated with nitrate assimilation is nitrate reduction in the cell. The analogy is Rubisco. So it's kind of the same analogy. Flux in, flux out, and one big fractionation. And that's the association of nitrogen, inorganic nitrogen being turned into organic nitrogen. Okay, so these factors, we have this ratio, and the relationship here tells us that there is a single fractionation mechanism that is dominating this nitrogen fixation. It's driven almost entirely by nitrate reduction, but the fractionation doesn't equal the nitrogen isotopic composition of nitrogen associated with nitrate reduction, that 10 to 30 per mil. So influx and efflux must play a strong role in that. We observe in the ocean, if we were to compare the profile of delta 18O in nitrate with delta 15N and take the ratio of those, we would get an observation of 1, similar to what we see in the laboratory. So what it appears is that growth rate is being modulated to give us sort of balanced growth, or the flux. The growth rates are maximized and efflux is minimized. So as nitrate, another way to put it is nitrate influx, that pumping of nitrate, that assimilation that active transport of nitrate is being very, very closely modulated, depending on how much is needed. So we have equal rates of all cellular constituents, so this balanced growth, and it maintains this major element ratio of 106 to 16 to 1. It's one of the major reasons why this Redfield ratio exists and is constant across the ocean. This nitrate transport into the cell is being regulated by the cellular needs. And so across the entire ocean, regardless of species, we seem to have a constant nitrogen isotope fractionation associated with uptake. But still, we can understand this in terms of flux in, flux out, and what controls that flux. In this case, the cells are using energy to control that flux. They need light to do it, so the only time we see a discrepancy from that 5 per mil fractionation is when growth is beginning to get limited by light. There's not the energy available, and so efflux increases. Okay? All right, so, but in most cases, that nitrate uptake, that transport into the cell is regulated to meet cellular demand, resulting in an influx to efflux balance to give us that 5 per mil fractionation. Yes? Does this carry over to freshwater systems? It ought to. Yeah. Okay, so we also have nitrate reductase used by bacteria for dissimilatory nitrate reduction. And this is some relatively recent data that looked at isotope fractionation in denitrifying bacteria as a function of cell-specific nitrate reduction rate. And what we see is an increase in fractionation with an increase in specific nitrate reduction rate, and then a plateau here. So 20 to 30 per mil, it depends on where this plateau occurs, but below this cell-specific rate, there's a change in fractionation. And again, guess what? You can understand this in terms of influx and efflux of nitrate and its control. So heterotrophic respiratory nitrate reduction accompanying production of N2 is described by this efflux model. With a fast cell-specific nitrate reduction, that there's a dominance of nitrate uptake into the cell, less loss. There's even less loss when the cell-specific nitrate reduction is low. We don't lose as much, so there's a greater utilization within the cell, and hence a lower fractionation. So a larger fractionation associated with nitrate reduction in nature is due to a faster cell-specific nitrate reduction rate. Okay. All right, so again, controls on nitrate denitrification, controls on nitrogen assimilation. Again, this efflux model holds. These are data from the Eastern Tropical Pacific. The Eastern Tropical Pacific was focused on in the studies by Karen Cassiotti and others and her students because they're one of the regions in which nitrite persists. We see nitrate concentrations in the ocean. We can measure them readily. Ammonium and nitrite, they're just difficult to measure. It either implies that, well, the implication is very, very rapid turnover. And there's rapid turnover of nitrite in the Eastern Tropical Pacific, but concentrations are high enough in which we can measure the nitrite nitrogen isotopic composition. And what's observed is an inverse kinetic isotope effect associated with nitrite oxidation. And it ranges from 9 to 21 per mil. It can be really large. In other well, we'll look at nitrite reduction in Anammox. It goes even higher under those conditions. But it means that the nitrogen cycling results in a really odd inverse kinetic isotope effect during nitrite oxidation. And here you can see the difference between the nitrogen isotopic composition of nitrate and nitrite. In a practical sense, if you're going to make these measurements in the ocean, you don't want both species present because your measurement is going to be a mass balance based on both the abundance and nitrogen isotopic composition of any nitrite present. And it's also, we're going to learn a lot about the nitrite, or the nitrogen cycling by looking at both the nitrogen and oxygen isotopic composition of nitrite in the ocean. It's telling us something about the reaction. It's telling us something about how complete that reaction is and how rapidly it occurs. And the person leading that is Karen Cassiotti at Stanford University. Most recently, well, a 2013 paper, this is the first and only paper I know that has attempted to begin to tackle and understand nitrogen isotope fractionation associated with anaerobic ammonia oxidation, or this Anammox. It converts ammonium and nitrite to N2 and nitrate. And what we see is, here's the ammonia pool, here's the nitrite pool. There's an equilibration of nitrogen between nitrate and nitrite. That's 60 per mil. There's a fractionation here associated with nitrate of 30 per mil, and between nitrite and N2 of plus 16. So an inverse kinetic isotope effect here of 16 per mil. Of ammonia, it's a kinetic isotope effect. It ranges from around 24 to 30 per mil. In effect, the net process will result in an increase in the isotopic composition of nitrate, which is one of the main tracers we use to sort of begin to gauge the importance of this reaction. Reactions like this in denitrification, it's very difficult to separate Anammox from denitrification, but the overall effect is very similar. We lose nitrate, and it changes the isotopic composition of nitrate such that it increases. So if we go back to this sort of instantaneous nitrogen isotope fractionation processes on this diagram, we should really consider both Anammox and nitrite oxidation as a mechanism that increases the delta 15N value of nitrate and that changes the isotopic composition of the residual nitrate. Okay, it's a complicated system. All right, one thing that we can use the nitrogen isotopic composition of nitrate to begin to estimate through time what the balance of these processes are. If we look at regions in which there's reasonably high production, where there's complete utilization of nitrate within the surface water, and where there's good organic matter preservation at depth, there's a really nice relationship, a one-to-one relationship between the delta 15N value of subeuphotic zone nitrate and the delta 15N value of nitrogen in sediments, so particulate nitrogen in sediments. And you can see that Cariaco, Gulf of Hanapec, offshore, or near shore, Oregon, Guaymas Basin, there's a nice relationship. So we can extend our interpretations back through geologic time in terms of the rough gauge of inputs and outputs based on the nitrogen isotopic records. Okay, so that's kind of a lot to absorb. Do you have any questions?
High Cariaco will have high production and high preservation.
Yep. It's really where that nitrogen is preserved in sediments. where it's not altered on the seafloor. And that occurs in regions where a lot gets delivered to the seafloor and where conditions are conducive to the preservation, typically lower oxygen conditions where it's not oxidized.